So in this video we're going to look at situation number 3 where we have both the sine and the cosine function in an integral having even powers, and in the particular case we're going to look at the sine is going to be raised to an even positive power. So the integral we want to resolve is the integral of the sine to the fourth of x dx. There's a sense in which we can think of the cosine as having an even power. This is guideline number 3 that we went over in video 1. If the powers of both the sine and cosine are even and non-negative, and in this case cosine is really an even power because it's cosine to the 0 equals 1. So we don't need to write the cosine function, but we really could consider this as being a case where both the sine and cosine have even powers. And the guideline indicates that we just want to make repeated use of the power reduction identities from trigonometry, and we want to continue to use it until we either get something that we can integrate, or if we wind up with an odd power of the cosine function, which could happen, then you just switch to guideline 2 from the previous video, which for this homework assignment I believe is video 3. So slide forward a slide so that we have more space. So if I'm going to work this one through, start off with the integral that we need to resolve. So sine to the fourth power of x dx, and what we really want to look at this as being is the sine squared of x all squared dx. So we have 2 times 2 is 4. We still have the same exponent going on, it's just written differently. And we have a power reduction identity for sine squared. So from trigonometry we learned that the sine squared of some input is equal to 1 minus the cosine of twice that input all over 2. So we step over here and we're going to take the sine squared and replace it with this. And the idea behind this is that we know how to integrate a first power of a sine or cosine function. So we're trying to get it to a position where we have only first powers so that we can integrate it using integration rules we've already learned. So here we integrate, we get 1 minus the cosine of twice whatever is inside of here. So it's going to be twice x, and this will be all over 2. And this has to be squared, so we get squared dx. And then if we square a half, this 2's in the denominator, so this is a half. We square that, we're going to get a quarter, and we can factor that 1/4 out of the integral. So I just squared the 2 in the denominator and then factored the 1/4 out. And then we need to square out this expression inside the parentheses. So we're going to get a quarter of the integral. We get 1 times 1 is 1. 1 times minus the cosine will happen twice. So minus 2 times the cosine of 2x. And then we get minus cosine times minus cosine is plus the cosine squared of 2x. And this is all dx. And when we look at this, we have a quarter of some stuff. We know how to integrate a 1. The antiderivative of 1 is just x. Minus, we know how to integrate 2 times the cosine of twice x. This is just going to be the sine of twice x. And the check on work would be to take the derivative of this. The derivative of the sine of 2x is cosine of 2x, but then the chain rule says take the derivative of the inside function. So the derivative of 2x would be 2. And so we would get back what we started with, so we know we integrated that correctly. The problem here is this is a cosine squared, so we're going to have to do more work before we can integrate this. So I'm going to go plus. I'm still going to be taking the integral of the cosine squared of 2x dx. But what I want to recognize is that I actually want to use the power reduction formula on this guy right here. And this is all a closed parentheses. So I could have done the power reduction formula already, just haven't. I'm going to do it as an extra step. It's not a big deal. So the power reduction formula for the cosine squared of an input is that you get 1 plus the cosine of twice that input all over 2. So we're going to make another replacement. So I've got this squared. I've integrated some already, so I probably it's probably good to put the plus the constant of integration in at this point. So I've got a quarter, just bringing my work up. So I've got a quarter of a bunch of stuff, and this is an x minus the sine of 2x plus, and now we've got an integral, but that integral is going to have some stuff inside of it. It's going to be 1 plus, and this is going to be the cosine of twice the stuff. So in this case, it's going to be twice what's already in here. So 2 times 2x is 4x. So we get 1 plus the cosine of 4x dx. And this is all over 2. And everything's times the 1/4. And then this 2 here can be factored out as a half because it's a constant. I factored out of the integral. Go ahead and integrate, so we get, and I still have my plus constant of integration, so I got a quarter of x minus the sine of 2x plus a half of some more stuff. We integrate 1, we get x. We integrate the cosine of 4x, we're going to get plus, we're going to get the sine of 4x. So the derivative of the sine of 4x is the cosine of 4x, but then the chain rule would say, ooh, we have to take the derivative of the inside, so we would get a 4. We would get 4 times the cosine of 4x. So we need a 1/4 out here that kills that 4 when we take the derivative, so that we get back exactly what we started with. Get rid of that underlining, and then close the parentheses. It's all times a 4th and plus the constant of integration. And we're pretty good right here, but we do have some x's that are like terms and probably should be combined and simplified. So one way of doing this, it's not the only way to do it, it's not the right way or the wrong way to do it, but one way to do this would be to recognize that you have a half times a 4th is an 1/8. So if I just come out here and I multiply by 8 over 8, which is 1, I could distribute the 8 into the parentheses. Give myself a little room here. If I distribute the 8 into the parentheses, I would get an 8 here. I would get minus an 8 here. I'd get 8 times a half. So 8 times the half would be a 4, and then I could distribute the 4 into the parentheses. 4 times x would be 4, and 4 times a 4th would be 1. And so if I do that, I've got everything inside the parentheses with no fractions, and I distributed this 8 in so I wouldn't have it anymore. So I have a quarter times an 1/8 this is a 32nd of, and I'd have 8x plus 4x, there's 12x's sitting in there, minus 8 times the sine of 2x plus the sine of 4x. So it looks kind of clean when I do it like that. It's not the right way to do it or the wrong way to do it. It's just nice and clean on the inside of the parentheses now. And it looks like we got it.